Welcome to this presentation of the paper Neural Network-Based Model Predictive Control with Input to State Stability. My name is Katrina, and I'll be presenting joint work with colleagues from Sintef Digital, Esten and Signe, and colleagues from NTNU, Jan and Kristin. We have considered MPC for systems where the dynamics are unknown, but where data is available so that learning can be used for building prediction models. Learning-based controllers and especially learning-based MPC schemes have been an active research topic for some years now and have been used for various applications with great success. However, for a lot of this work, stability guarantees are still really hard to make and is missing from a lot of references on learning-based MPC. In this paper, we consider how a neural network can be used as a prediction model in MPC and analyze stability of the resulting closed-loop system. We consider nonlinear discrete time systems of the following form, where Y is a scalar output, U is a scalar control input, and W is noise on the system's output, assumed to be bounded and lie in a compact set. Our state vector has the following dimension, and the system dynamics are modeled using a nonlinear autoregressive model with exogenous input, for short NARCs. And for this model, the next output of the system is a function of previous outputs and inputs. And here, my is the number of previous outputs, while mu is the number of previous inputs needed to describe the next output of the system. We also consider hard input constraints and soft output constraints, and we reformulate the NARCs model to a state space representation, which we will consider in the MPC algorithm. Our control objective is to steer the system from random initial conditions to a desired reference equilibrium point. As mentioned earlier, we consider the case where the system dynamics are unknown, but we have input and output data available. The data is used for training a NARCs neural network, i.e. the neural network will approximate the function f. When we train the neural network, we will have previous inputs and outputs available, and this means that we can train the network as a conventional feed-forward network. Whereas when we are making predictions, we do not necessarily have previous measurements available, and we need to feed back the network's own estimate of this output. And this introduces feedback in the neural network, giving it a recurrent structure, which is also illustrated in the figure on this slide. We then formulate the following optimal control problem, for which we want to minimize the following expression over some finite prediction horizon given by big N for some initial condition of our state vector. And this results in a sequence of control inputs, U, where we want to implement the first element. We use the learn prediction model here formulated for the NARCs state space system given by big estimated F. And we use this to predict the open loop behavior of the system. The optimal control problem does not include a terminal constraint. Instead, we use a design parameter lambda, which is equal to or larger than 1, to weigh the terminal cost df. The total stage cost L consists of a standard quadratic function that penalizes deviations from our reference state and our reference input, and is also added a barrier function to account for soft output constraints. And the optimization problem is subject to hard input constraints, and here Y is the predicted output of the system. In order to analyze stability, we define the prediction error and let this be the difference between the true output of our system and the predicted output provided by the NARCS network. And again, W is noise on the system output. We then define input to state stability as the norm of our state being upper bounded by some class KL function beta and a class K function gamma, according to the following expression. And here X naught is the initial condition of our system, and EI is the largest prediction error. In order to prove input to state stability, we will make in total 4 assumptions. I will briefly address them here and refer to the paper for further details. And first of all, we assume Lyapunov conditions on the terminal cost VF in the terminal region. Secondly, we assume that the total stage cost is a positive definite function. Furthermore, that the prediction error is bounded. And finally, that the nominal prediction model, that is the prediction model with no prediction error, is uniformly continuous. And the 2 last assumptions, they are both related to the learned prediction model. And the prediction error encompasses both the approximation error as well as the measurement noise. As previously stated, the measurement noise is assumed to lie in some compact set and is therefore bounded. And assuming also that the approximation error is bounded can be a fair assumption if the training data used to learn the prediction model is representative of the data that will appear in closed loop operation. Because then if the prediction error is bounded on the training set, we expect it also to be bounded for data seen in closed loop. The continuity requirement to the prediction model is for the NARCS network related to the continuity of the activation functions selected in the layers of the neural network. And for NARCS neural networks, we typically apply the sigmoid function that satisfies this requirement. Having established the necessary assumptions, we now consider input to state stability of the following closed loop system, where big F is the true NARC state space system, xk is our NARC state vector, kappa MPC is the control input resulting from the optimal control problem, and finally, ek is the prediction error as discussed. The procedure of the proof is first to show nominal stability. So for a case with no prediction error, we will show that the closed loop system is asymptotically stable. And we do this using an adaptation of results from reference number 1. After we show that the closed loop system is input to state stable with respect to the bounded prediction error, which is done using an adaptation of results from reference 2. We have implemented the proposed control design for a benchmark system, namely the continuously stirred tank reactor, or CSTR. And we have tested the learning-based MPC scheme for 100 simulations, testing different initial conditions. And in this figure, we have plotted the one-step prediction error, or more specifically, the mean and 1 standard deviation above and below the mean for the simulations where we use the learning-based MPC scheme to control the system to some desired set point. In order to compare the closed loop performance of the learning-based MPC scheme, we have also implemented an ideal MPC scheme, here understood as using the ordinary differential equations to predict the output of our system. And we ran both controllers for the same 100 initial conditions and have here also plotted the mean as well as the standard deviation for the simulations. And for the implemented simulation example, we see that the closed loop performance is quite comparable. In order to summarize and conclude, we have considered a learning-based output feedback model predictive control scheme, where the prediction model is learned from input-output data using a neural network. We have then looked at conditions for which the closed loop system is input to state stable with respect to the prediction error. And finally, we have seen simulation results testing the proposed control design for a benchmark system, namely the CSDR. And we have compared the performance of a learning-based and an ideal MPC scheme. And finally, these are the cited references in this presentation. And with that, I would like to say thank you very much for your attention.